Um, Today we are going to see the different kinds of controllers that you can use. We have seen how a simple feedback loop is made, and right now I would like to discuss the different types of controllers that you can use, whether you use uh, the root locus method or frequency response method. The types of controllers are important to know what each one does, and that's what this lecture is about. So let's take a look at the basic control loop, and then we will look at the different kinds of controllers, and our objective is to do some examples as to what each one of those controllers do. So here let's get started and look at for the kind of controls that we can have. We can have a closed loop control system or an open loop control system. We're discussing today the closed loop control systems and some very basic concepts. We, of course, want to design a control system. A control system is purpose is to regulate or adjust the flow of energy in some desired fashion. The closed loop control uses measurements of the output to modify the system actions to achieve the desired goal. If you have an open loop system, does not use any measurements or feedback, adjust the flow of energy according to some schedule that we have. Automatic, for example, open loop would be, for example, the operation of the sprinkler systems in your house. That would They come at a certain time and then they go off at a certain time. It's open loop system. Closed loop is if you measure something and then you do something so that the system actually does what you want. An automatic control, of course, acts automatically without outside intervention. So in doing the models, we know now that we can reduce them to a single transfer function or a state space form. So this is the most general form of a control system that we can have. We can have a few, we can recognize rather a few blocks, like this is our main block because this is the plant. This In this picture, I have listed all this um, with the names. This is this is our system, and everything around it deals with the control. So these are all the components that you can have. You can have from this and just one proportional control system, and like we have seen previously, or you can have the different components like you see in this picture. If you measure the variable of interest and you put it through a feedback loop, that variable is compared with this reference, and the difference between these two produce an error. And then, of course, the inside this this block in here, we produce this error, and this becomes the compensator or control system. So that's another word we use. Compensated system means that you have some sort of a control block in there. This one in here measures the disturbance of the system. Like, for example, if you are trying to control the temperature of a room and somebody opens the door, that would be considered a disturbance. So the disturbance modifies the input to the system and messes it up. So you need to go to the feedback loop, compare it again, and compensate it again until this will adjust. So the H of S is the feedback element. This output of this variable that you have in here, QoS, is a modification to the disturbance, but normally we just use this directly, this signals. So this is the uh, feedback signal, this one right there. This would be the output, this would be the disturbance input right here, and you have the error signal, of course, and this would be the variable that is controlled. This is the reference input in here, and in here would be the control, the command input here. So normally this would be like a dial, and this is already like converted to a voltage, some signal. So, okay, having said this, in the control laws, when you have a response to a step input, for example, we recognize several aspects of this. Like if this is the where it's supposed to settle down, this will be the maximum overshoot, and this would be the band for the setting time. And if there is a difference in here values, that will have the steady state error. So in here we have the objectives to minimize the steady state error. We would like to minimize the settling time, and we want to achieve other specifications such as minimize the overshoot and things like that. So you have the category, for example, of two-position control. You have a proportional control. The two-position is on and off control system. Like I told you, it's like the sprinkler system on your house or the thermostat in your room. That's the same way. The proportional control is the one that just changes the value of k, as we saw in the previous lecture. The integral control and derivative control, those are the basic ones, and there is a combination of one of these which is called the PID controller, which is proportional, integral, and derivative control. So let's take a look at each one of these. So the first thing is that you have the two-position control system, this one. In here you have a situation where you have you turn it on and then you turn it off. It has this the only objective is either on or off. So either it turns, for example, light if a level control is low, or no, that's not a good example. The best example is the timing, the timer thing, even for your Christmas light, that kind of thing. In this case, for example, if the level of this water in this tank goes down, just like you have it on the a toilet tank would work like this too. So in this case is an electromechanical switch, and normally we only have just a hydraulic system with would be hydromechanical. That's the way most of the toilets tanks are. But this one is electrical. See, the float goes down, closes the circuit, and then activates this valve to either put more water or to stop the flow. So normally it goes like this. This would be the normal behavior of this, like a liquid level control system. So in here you have a dead zone, as it's called. It's never, you cannot switch immediately like this. For example, the temperature controller. Here you have an oven, the kind that we use for Thanksgiving. Put your turkey inside in there, you put the temperature in there. So there's some sensors in there. Now you can relate to it. There's temperature sensors even on the turkey just to make it, that would be an open loop system, right? So you have them a couple and pops up when it's done, and that's just a switch on and off. But to maintain the temperature in the oven, that's a different thing. That one is a closed loop system because you have a sensor, feeds back what's going on. This is the command here where you have your dials where you want a certain temperature or a certain time. And so you have in this this is the the control unit itself. That actually takes action and gives more power here so that it heats up or stays off to cool it down. Another thing that you consider here are the insulations from the walls, but this would be a kind of system that we have a differential equation of first order like this, derived from the basic application of principles and heat transfer. And then you will have the amplifier circuit function, of course. And this would be something like this. No, here. But the output is a steady state plus this control. So the temperature controller here, if you have these equations, this equation is the one that controls this one. And you have a block diagram like this, where you have a transfer function in here, you feed back in here, make the comparison. So that modifies the input to the controller. And this would be the input into the system if there's no disturbance. Okay, this is the disturbance right here. So what are the important design parameters? Time constant, that indicates us how fast the system is. The damping ratio to see how much damping we have. And of course the natural frequency. We would like to look at the systems for the speed of response as well as how accurate they are. So in here we have a closed loop system of the kind that I am talking about, where you have, in this case, this would be position control. Like for example, if this would be to maintain certain part in the vertical position. If it starts to tip, then you need some control to bring it back or bring it forward. So the proportional control, like I said, you have the plant, and then you have the controller. This. Okay. If you write the equations for proportional control um, of this particular example, you will get an expression like this. And or like this. And you have the simplification of this. So this is much more simplified than if we only have k. But this is the proportional control. I told you there is three of them: proportional control, integral control, and derivative. So in the case of proportional control, a change of the speed, for example, can be simulated by a step input for the angular velocity if it's rotating. So this would be the input here. So and then what's the output? And now you have this using an individual step function. And so you can have just one step function and see what the response is. In summary, the proportional control usually used with the first order systems. The output never reaches the desired value if there is some resistance. And you choose the gain k, and then it needs to be strong enough to offset the error and correct it. The output approaches the final value without oscillation, so it's very good to in the final time, the final as a steady state. But the problem is that a, there is a steady state error, and so if you keep only proportional control, you are always operating with some error. Now, if you have integral control, on the other hand, this is manifested by 1 over s times some constant of integration. And this would be like in using the S domain, this would be like the time domain. But in this case, you have something like this. This is your system, and then this is your integral controller. So this is an example of a velocity control system where you feed back the velocity and then you calculate the difference and then you apply power. This is typical case of a cruise control, right? That's how it works. And then this is the loop. As you can see, the plant, and then you have the integral control over here. What are the characteristics of this controller? One, the system tends to oscillate a lot and could become unstable. Then the other consequence is the final value theorem cannot be applied. Third, the integral control improves the steady state error, but it produces unstable system in the example prior. Integral control will degrade the transit performance because the system oscillates. So you don't want lots of oscillations as you are trying to control, but it gets rid of the error. And finally, there is derivative control. When you have derivative control, you can also modify the input to the system, and in here in the integral control produce um, some signal error, and in this case we would like to make a controller react to the derivation of the error with some derivative control law. This is used to dampen oscillations. So you see each one of the controllers has a plus and also has a negative. The proportional control is very fast, but you end up with a steady state error. The integral control gets rid of the error but makes the system oscillate. And the derivative control puts damping into the system and therefore damps the oscillations in this case. So you can have a control law which would be proportional and derivative control, or you can have a PID controller which means proportional, integral, and derivative control. So tweaking these three is an objective of doing design of control systems. So if you have, for example, in here, you have the system, this is like a servo mechanism, and this we want to improve the transient response over the proportional action. We have the integral action is not required in this case, just proportional derivative, and then that would be over here. Yeah, so these are this is the summary of this derivative control system. So this is stable for the values that we're giving here. Okay. You see a couple of other conclusions on the bottom of the slide relating to the correct action and the steady state results. Zero offset error. So you have a disturbance in there, but this one, PI controller, you can see proportional controller produces steady state error. Integral control corrected the error, but degraded the transient response. If you combine the instantaneous response of proportional control with a zero state error with the integral action, that's what I'm trying to do here. So this is the proportional side, this is the integral side. And I have to enter it as a control law, because that's what MATLAB is going to look for. In the case of the consideration of the damping ratio, we need to tweak the derivative and the proportional control in such a way that we will damp the oscillations. In this case, you have an example of a system, like here's the velocity, but you integrated is the position control, and you have a overall feedback loop and one feedback loop for the system. Okay, so this is the PI controller, for example, first order system. Steady state is stable for positive values of k. Offset error is 0. And if you respond to the unit step, disturbance is also 0 at steady state. Okay. So this is the way we'll implement the damping ratio. So PI controller, you have a transfer function like this, one for the position, the other one is regards to the disturbance. Steady state performance is good if K and K sub I also TSC, CP, and CIP bigger than 0. For a small e, Kp must be large in order to satisfy the equation. It's not too hard to, it's difficult to do. If Kp is bigger than 0, the constant may not be satisfactory. And then we will use a third order equation done using Root-Locus method. All right, here's the liquid level control system. This is a little more sophisticated. And here you have a tank, and of course the valve and our output here. But this one has pneumatic control combined with a mechanical system. So if you have this pipe, this tube that goes to this lever here that you see, so if you increase the pressure here, this would go in here and it would make it go like that. Okay, then this thing rotates, this one comes up, okay, and so once you activate this, then it activates this pressurized system and then activates the valve, whether it's to open or close. So it's a little simpler than it looks. And then you can see that we can linearize the system to analyze it, or nowadays using MATLAB we could directly you could directly do do the calculations. Okay, so this is the way all the blocks in this example will stay at this time. What I'm trying to tell you is that here the different kinds of controllers that we put in is our main focus here. Finally, there is the so-called PID control, which stands for proportional, integral, and derivative control. It means it has the characteristics and the ingredients for each one of the controllers that whether you want to dump the oscillations or you want to be precise, all that stuff can be done with a PID controller. In summary, you have any combinations of the controllers that can be done depending upon the system. You have PI control, which is proportional plus integral. You have PD, proportional plus derivative control, or you have PID control, which is a combination of all three. So these values of K are important in there. Okay. So depending upon the action that we want, the gains are adjusted to achieve the desired control action. Okay.